So hi there and welcome back to Triplicate. And in the last video I did, which was the battery charger circuit test, I tried something new as well as the pointing down camera, which is that which lives just up there. I tried using my tablet to get a shot across the bench so I could switch between a close-up of what my hands were doing and wide angle of what I was doing, so if I was reaching over you could see. But I did have a bit of a problem in that the autofocus on the tablet kept trying to refocus and jittered the image in and out. Most annoying. So before we actually get started with the main event for this video, just like to pass on a little tip I found after a bit of digging. So we will take a box which we're going to get the tablet to focus on, and I'm not going to set up a camera to show me doing this, but what I am now doing is tapping and holding the screen. So now a little icon has appeared, grey, so it took me a bit of hunting to find it, saying AF. So now the focus should be locked, and the reason that white box was on there, hopefully it should have focused on that while I wasn't here. So now hopefully the focus shouldn't jitter in and out. We hope. We shall see when we look back at this video. So on to today's main event, which is the main green. It's been a while since we've had a look at this. We're going to have a look at it now. So the last time we were trying to implement the code I'd written for the tutorial, which ran on the PC. We were trying to implement it in the STM32, and we found it ran too slow. And while I was ferreting around trying to make it run faster, I discovered, somewhat to my embarrassment, that this guy has a floating point, hardware floating point engine built in it. So I finished it there, and in the last tutorial we went all over to floating point. So I'm now going to port back into here floating point code, and we are going to try that. So without further ado I will start typing. Okay, so here we are looking at the two bits of code. On the right we have the new version of the code, and on the left we have the old version of the code, and we're just looking at the oscillator structure, and you see the inputs, which are parameters, are the same, but the parameter code has changed as well, and things like the pitch are now in floating point instead of 32-bit integer. Interesting thing to note is that the wavetable pointer, i.e. the wavetables, are still in 16-bit integer format, because we just don't have the ROM space to put them in 32-bit format. But the STM32 seems to convert in a single cycle, seems to load an integer into a float without having to do any conversion code, so that's fine. So that's it. I will crack on and update the STM32 code to be the same as the PC code, and I will bring you back and we will see how it does. Okay, so I've got the test audio running, and that is the time it takes in the audio calculation. One trace for each half of the buffer, and to prove it, there we go. Well, there's one channel of the test audio. So now if I go into the main code, disable the test audio, Stop that. Run debug. We're there. Fire her up, look at the scope, and whoops, only one channel is working, and it should take about 650 something microseconds to calculate one buffer, about there, and it's taking too long. So I have some considerable work to do still to try and persuade it to run at a speed where we can at least get one voice out of the thing. So I shall have to take the code apart piece by piece and test each piece, see how long it's taking, and see if I can speed it up. And I will hopefully bring you back at some point with some good news. Okay, so we're going through the oscillator code. This is the oscillator do function. I've commented out these parameter calls because we'll look at parameters later. So let's look at this bit of code, which is to do with calculating the phasing first. So I have put a breakpoint at the start of that code. So if I fire that code down and stop at the breakpoint, run debug, and hit go, it stops at the breakpoint. And now here we have a disassembly. Now I've no wish to get into writing ARM assembler if I can possibly help it, but at least it'll tell us what the compiler's doing, and we can see straight away that it's actually, and I'll give you a bit more of this to look at, calling some functions here like extend-s, fdf2, and sub f3, and another extendf. So that will slow us down. And if we look here, this is just GCC GNU reference. We look here, extend SFDF2 is turning our float into a double, so it's all trying to do all these calculations at double, which we don't want, because then it'll have to call a function to do everything, whereas we want to do multiplications things in a single cycle using the hardware floating point engine. So I now have to go away and find out why the compiler is doing this and essentially stop it doing it. Okay, so woe is me, for I have fallen for one of the C language's quite a few eccentricities and annoying features. So here you can see I've taken half the calculation just so we can see what the compiler's doing. Now, what you would think would be a logical way of doing this calculation in terms of the types of variables would be to say phase inc is a float. So if any of these quantities that we are involving in this calculation are not floats, we will convert them to floats and then do the calculation using them. Unfortunately, in C this is not the case. It seems to take the first quantity this side and do the calculation at whatever that is, and then convert the result to this side. And here is the disassembly for what we have here, and as you can see, it's calling all these double precision floating point handling functions, and back at the end it calls this truncate function to truncate double back to float. And why is it doing that? because of another little C language thing, I've put 1.0 in, but what is it assuming, what type is it assuming that 1.0 is, a float or a double? Well, it's, for whatever reason, assuming it's a double. There may be a setting somewhere that can change that. So what we want to do is turn it into a float simply by putting F at the end. So if we now recompile it and upload it, there we go, and run it round to our little breakpoint. So line 59, here we can see it's not calling any of those double functions anymore. It's so I have to go through all the code looking for explicit floating point constants and making sure they have an F after them. And having done that, I'll try and run the code again and we'll see how much faster it is. So I've got here a little table of the timings on how long the oscillator code takes. So this is the time for, well, the whole voice, but it's only one oscillator at the minute, to generate 32 samples with no parameter calculations, and the maximum possible time to do this is 667 microseconds. So that would leave no time left for any of the other stuff like the pots and the display, so we can't go that high. So as ported, the PC code took about 100 microseconds. And just for comparison, I generated a really crude, possibly the simplest oscillator code I could, and that took 10 microseconds. So most of that 10 microseconds is the overhead of calling the voice function and the for loop and so on. So the code we have running here is the code where we forced it to do everything in floating point and got rid of all the double precision stuff that was calling functions, and that is about 42.5 microseconds. So what else can we do to reduce the time this all takes to run? Well, we can make the functions in line. So instead of doing whatever it needs to do with parameters and then jumping to a subroutine and then jumping back, it just writes the code in series. Now that's not a problem because the oscillator, because it's called in from one place in the voice. What am I doing? But the oscillator calls oscillator get waveform, which is here, and it calls it twice. So if we inline this, that code is going to get put here and here, but it's not a big function and we've got plenty of code ROM, so we are going to go with inlining that like that, and we are now going to see how that does us. Okay, we're done, so let's fire her up and go back to the scope, and should we see what our time is now? 37.5. So not a huge game, but worth having, Now another way you'll get code to run faster, certainly back in the day, was to use registers for local variables in functions instead of letting them create memory space on the stack and then have to load and save them off the memory. Now the STM32 has loads and loads of registers, so it tends to do this automatically anyway. However, here we go, I've put all the local variables and parameters in these two functions to registers, and I've compiled it and run it, and we go into the picoscope and we look here, and 37.26, 37.5, as near as we can measure it on this scale. So that's not gaining us anything, and the reason being, if I put a breakpoint there, oh, it'll nicely stop at it. If we look at all these here, it says optimized out, but if we step through, should do this. There we go, it's actually created a value for tab index, which is 60. So that is about as far as I want to go with the oscillator for the moment. To make any more improvements, I'd have to go in and see if I could make the algorithm more efficient, which I might end up having to do, but for now we're just going to see what we can do to make the code run more efficiently. So now let's look at parameters. Now this oscillator has two parameters, the modulation parameters, and it updates those every time the oscillator is called, and we've commented them out. So that's our baseline, which is 37.3 microseconds. So now let's put these two parameters back in and compile and run that and see how much that time they're taking. Debug, and off we go. Right, we're done, so let's fire it up. Okay, let's look at the picoscope. Okay, so that is not good, that's taking a lot of time. So if we go to here, that's 157.5 microseconds. So we need to try and reduce that if we possibly can. Okay, so I've put a breakpoint in, stepped into this function, and the first thing we see is down here we get to line 44, and it's calling the extend function, so it's trying to do a lot of stuff at using double precision instead of floating point again. So let's look at the culprit, which is, I guess, param resonant filter damping, which is a constant declared here. Oh, and there's param resonant filter gain as well. So let us just stick a cheeky little F on the end of those. Okay, so let's run it. It's found my breakpoint, so should we just go in the code for now? And that looks good, and it's stepped out of it. So we think that solved that problem, so let's let her run. So that's taken us back to 77. Okay, so I've discovered, I think, a good way to save some coding time. The input sum variable is currently declared in the parameter structure. However, if we look in the function, it's actually only ever used in parameter update mod. So you can see what I've done here. I've actually declared it as a local variable. So let's see how that does. And I've already compiled it and run it. So we get into here, and here we go. So that is around 74. So that doesn't gain us a great deal, but it's certainly better coding. So shall we try and inline this function and see what that gains us? Now I'm a bit reluctant to do this because it's called from lots of places, so inlining it is going to mean its code is repeated many times. But let's for a minute assume we have plenty of code ROM, and we will do that. Right, a bit on inlining here, because it's actually not something I've ever really used. It's the last synthesizers I did were written in DSP assembler, and since then I've had processors which have had plenty of power, so I hadn't needed to do this process of trying to make things run faster. And when we did the oscillator, we just called the function inline and it worked fine. But that's because certainly these functions, the get waveform function, was in the same file. Now the parameter update mod function is in the parameter.c file, and it's used in oscillator.c and other places. So when the compiler is compiling oscillator.c, it looks in parameter.h, and if the function's a normal function you call, you just tell it the format of the function. It's happy, and it's up to the linker to actually find the function and check that the declaration is valid against the function body. Inlining, it's different. Because the compiler needs to write the parameter update mod function in amongst the oscillator code, this code here must be available to the compiler when it's compiling oscillator.c. So if we are putting this function in line, we do not declare it here. Because there's no point in making a piece of code that it's never going to call. Instead, in parameter.h, which remember is included in oscillator.c, we don't want that anymore, we now declare it is in line there. So that code is available to the compiler when it compiles oscillator.c and filter.c and the other files that call this function. So we should be ready. Shall we? Okay, ready to go. However, we are going to put a breakpoint there to check these functions are actually inlined as we anticipate. And yes, they are. So that's working all right. So we are going to run it and see what that gains us. Back into the trusty scope. 73.5. I don't think that's gained us anything. Okay, so that's the whole of the voice code now running, and I just went through the rest, and as I did in the oscillator, got rid of any bits where it had decided to do the calculations at double precision, and inlined a few of the functions. And if we look on the picoscope, that is not good. That is 394 microseconds out of 667. So basically at the minute we're looking at a monophonic synthesizer, which I have to say is pretty disappointing. I thought we'd get a few notes polyphony out of that processor. So what I'm going to do now, I haven't actually tested the code to see if it's actually synthesizing, so I'm going to do that, and assuming it isn't, I'm going to fix the bugs and hopefully at least bring you back to show you it working. Okay, so it runs. Just had to set up all the parameters to some sort of sensible value, and off we went. So here we go. One synthesizer working and playing. Even that's up because none of these guys do anything and the display doesn't do anything, so I guess that's the next task. Get the voice editing working. Okay, so here's recording straight into the computer, so not trying to listen to it through camera quality, and I will also put a downloadable copy of the WAV file so you don't have to suffer YouTube's audio processing. So let's give it a whirl. So I think it sounds pretty good. So I think I'm gonna wrap it up here for this video. Well, it's nice to actually get a synthesizer working and actually play from a real keyboard for a real MIDI. However, it is somewhat disappointing that, as it currently is, it's a monophonic synthesizer. And I was hoping for hopefully 8 notes, so I got that considerably wrong. However, we will press on, and as I said, I guess the next job is to get the front panel working and get some of the sort of storage so we can program voices in, and we've also got to finish the synthesizer off. There are a few features yet, but they will come in after their appropriate video in the synthesizer tutorial. So for now, that's it. So it's goodbye from Triplicate, home of interesting electronics. Goodbye.